Alright, so in this video I'm going to be talking about few-shot learning, but we are dealing with a real problem because many papers ignore the fact that source domain and target domain usually don't have any kind of overlap. So we should create something that we call in transfer learning domain adaptation in order to share different understanding and different when we go from source domain to target domain, it should be adaptive. So I'm gonna be focusing on this paper in 2021. Existing few-shot learning methods make the implicit assumption that the few target class samples are from the same domain as the source class samples. However, in practice, this assumption is often invalid. The target classes could come from a different domain. So no overlap, no intersection. This poses an additional challenge of domain adaptation with few training samples. Even if you want to do classically the domain adaptation, you have problems because you have very few samples. So in this paper, the problem of domain adaptive few-shot learning is tackled, which requires few-shot learning and domain adaptation in a unified framework. So we should solve them in a unified frame. So we propose a novel domain adversarial prototypical network, and it is designed to address a specific challenge. The domain adaptive objective means that the source and target data distributions need to be aligned, typically through a shared domain adaptive feature embedding space. This is the typical paradigm in domain adaptation in transfer learning. But the few-shot learning objective dictates that the target domain per class distribution must be different from any of the source domain, meaning aligning the distribution across domain may harm few-shot learning performance. However, how to achieve global domain distribution alignment while maintaining source target per class discriminativeness thus becomes the key. So our solution is to explicitly enhance the source and target per class separation before domain adaptive feature embedding learning in order to alleviate the negative effect of domain alignment. So we go from source domain into a target domain. For example, your target domain could be totally like cartoonish, but the source domain has a different distribution. So in more extreme case, the source classes could be captured in photos and target ones in sketch or cartoon images. This means that the visual recognition model trained from the source classes need to be adapted to both new classes and new domains. Think about it as in natural languages is even harder because, for example, you say a very complex sentence, but in the target domain you have a very summarized in terms of dependency parsing, everything is much more summarized. So it's even harder in NLP if you want to do domain adaptation, especially with very few samples. So this is an overview that we have source and target, we have discriminative, we have adaptive reweighting. Then we do the classical prototype learning. And then we have domain confusion coming here to the adaptive reweighting. But we have domain discrimination loss. So we'll go through different components of that. So we have a data set, and you know that source and target, they don't have any intersection. So we create the support and query for them. So in prototypical network, you just take the average. Just take the average and you get the prototypes. And it's very easy to do that. But with the above class distribution, the loss function over each episode is defined based on negative log probability. Similarly, the loss function over each episode can be formulated based on negative probability of query sample with respect to true class label C. Now we are talking about domain adapt adversarial, because as mentioned before, the main objective is to learn a feature embedding where the global distribution of the source and target domains are aligned, while the domain-specific discriminative information is still kept. So we choose to enforce domain discriminativeness and domain alignment learning objectives before and after an embedding module. The task of balancing these two objectives are then handled by an adaptive loss reweighting module. The input to the embedding module is the output of feature extraction. The embedding module consists of an autoencoder and an attention submodule. So the autoencoder takes f tilde as input and output the vector, embedding vector. To enforce f to be domain confused as possible, we impose an attention submodule composed of a fully connected layer. So the attention is core. This fully connected, when you give the f tilde to this fully connected layer, is used to remove any domain-specific information. So combining the autoencoder and attention submodule together, we have the final output of the embedding module. So although both the autoencoder and attention submodule can implicitly align the two domains, further alignment is needed by introducing domain adaptive losses. But motivated by this conditional domain adversarial network and the domain adaptation network, so it's kind of adversarial network that you're using conditional domain adaptation. We define a domain adversarial loss on the domain discriminative across the source distribution and target distribution. So this is our target distribution. We draw from that. This is the source distribution we draw. So it's typical adversarial, but our domain, because we go from source domain to target domain, so that produces some confusion, some adversary. And we can learn that adversary. So f and g, let h be joint variable of feature representation of f and classifier prediction. The multilinear map is chosen to condition d and g, which is defined as the outer product of multiple random vectors. However, multilinear map faces dimension explosion. The multilinear map has a dimension of d sub f times d sub g, which is often too high dimensional to be embedded into deep learning. So to address the dimension explosion problem, the inner product can be approximated by the dot product. And so finally, we adopt the following conditional strategy, where d sub phi denote the dimension of a fully connected layer. And for domain adaptation, we just solve, as I said, this min-max. And the sub-problem, which is max of E, is solved by adding a gradient adversarial layer. And the sub-problem of mean E is solved with the standard backpropagation. So this part is standard backpropagation. Note that some samples are easy to transfer. while others are hard to transfer. If the loss function imposes equal importance for different samples, it could weaken the effectiveness of the learned model. We thus modify the original formulation by adopting the entropy criterion, where C is the number of classes and G sub C is the probability of the sample belong to class C. We reweight training samples by an entropy-aware weight to make easy to transfer samples priority to hard ones. The loss for learning domain-confused feature representation is this. Note that the domain adaptive confusion loss is useful for bridging the domain gap between the source and target, but it has the unwanted side effect of over-alignment at per class level, which will harm. So to alleviate this problem, they introduce a domain discrimination loss so that the per class distribution within each domain is different from each other. Note that there is already a domain discriminator for domain alignment after embedding via gradient reversal, so it makes little sense to add another on the same embedding space. Instead, a domain discriminative loss is added on the output of the feature extraction, CNN. So we first define a conventional classification loss on the domain discriminator across the source distribution and the target distribution, as well as on the feature representation before feature embedding and the classifier prediction. The loss for learning domain-specific feature representation is this. So it is trained with multiple objectives, which can be seen as a multitask learn. So it is more crucial to balance among them, especially since the different episodes, different recognition tasks are sampled, which pose different level of demand for this competing learning objective. A naive weighted sum of losses thus does not suffice. So more sophisticated adaptive loss reweighting mechanism is required. So we adopt an adaptive multitask loss function based on maximizing the Gaussian likelihood with task-dependent uncertainty in order to determine the weights of objective automatically. So let the output of the neural network model with weights W and input X be this one, and the discrete output of the model be Y. So we utilize the classification likelihood to squash a scaled version of the model's output with a softmax. So specifically with a positive scalar, this scalar, sigma, the log likelihood, can be written. So with a positive scalar sigma, the log likelihood can be written like this. And our DAPN has 4 discrete outputs. So it is modeled with multiple softmax likelihood, respectively. And the joint loss is the joint loss, because we have 4 outputs. So the adaptive weights among these 4 losses are directly defined.